Good afternoon, class. Welcome to Math 2129. That's business calculus. Today is the 15th of April, and we're going to be looking at exponential functions. Exponential functions. Exponential functions. So, what is an exponential function? An exponential function is one that has a power in it. So 2 to the 4 is an exponential function. But we're going to be looking at a special type of exponential function. We're accustomed to things like x squared, which is another type of exponential function. Now we're going to be looking today though with the variable being the exponent. So for example, 2 to the x is one of the exponents we're going to be looking at. So what does 2 to the x look like? Well, we're going to take a look at a video, and we're going to use that video to help us to understand what exponential functions look like.
We're asked to graph y is equal to 5 to the x power. And we'll just do this the most basic way. We'll just try out some values for x and see what we get for y, and we'll plot those coordinates. So let's try some negative and some positive values, and I'll try to center them around 0. So this will be my x values, this will be my y values. Let's start first with something reasonably negative, but not too negative. So let's say we start with x is equal to negative 2. Then y is equal to 5 to the x power, or 5 to the negative 2 power, which we know is the same thing as 1 over 5 to the positive 2 power, which is just 1/25. Now let's try another value. What happens when x is equal to negative 1? Then y is 5 to the negative 1 power, which is the same thing as 1 over 5 to the first power, or just 1/5. Now let's think about when x is equal to 0. Then y is going to be equal to 5 to the 0 power, which we know anything to the 0 power is going to be equal to 1. So this is going to be equal to 1. And then finally we have, well actually let's try a couple more points here. Let's try out, extend this table a little bit further. Let's try out x is equal to 1. Then y is 5 to the first power, which is just equal to 5. Let's do one last value over here. Let's see what happens when x is equal to 2. Then y is 5 squared. 5 to the second power, which is just equal to 25. And now we can plot it to see how this actually looks. See how it actually looks. So let me get some graph paper going here. My x's go as low as negative 2, as high as positive 2, and then my y's go all the way from 1/25 all the way to 25. So I have positive values over here. So let me draw it like this. So this could be my x-axis. That could be my x-axis. And then let's make this my y-axis. Draw it as easy as I can. So let's make that my y-axis. And my x values, this could be negative 2. And my y-axis keep going. So that's y. This is x. It's negative 2. It's negative 1. That's 0. That is 1. And that is positive 2. And let's plot the points. X is negative 2. Y is 1/25. Actually, let me make the scale on the y-axis. So let's make this, so we can go all the way to 25. So let's say that this is 5. Yeah, a little bit smaller than that too. So this is going to be 5, 10, 15, 20, and then 25 would be right where I wrote the y, give or take. So now let's plot them. Negative 2, 1/25. Negative 2, 1/25. 1 is going to be like there, so 1/25 is going to be really, really close to the x-axis. That's about 1/25. So that is negative 2, 1/25. It's not going to be on the x-axis. 1/25 is obviously greater than 0. It's going to be really, 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 really close. Now let's do this point here in orange. Negative 1/5. Negative 1/5. 1/5. 1/5 on this scale is still pretty close. It's pretty close. So that right up there is -1/5. And now in blue, we have 0, 1. 0, 1 is going to be right about there. This is 2.5, that looks about right from 1. And then we have 1, 5. 1, 5 puts us right over there. And then finally we have 2, 25. When x is 2, y is 25. 2, 25 puts us right about there. And so I think you see what happens with this function, with this graph. Starts off, the further negative, in the negative x, the further in the negative direction we go, 5 to ever increasing negative powers gets us closer and closer to 0, but never quite. So we're leaving 0, getting slightly further from 0. Right at the y-axis, we have y equal 1. And then once the exponent over here, or right at x is equal to 0, we have y is equal to 1. And then once x starts increasing beyond 0, then we start seeing what the exponential is good at, which is just this very rapid increase. Some people call it an exponential increase, which is obviously the case right over here. So then if I just keep this curve going, you see it's just going on kind of this, sometimes called a hockey stick. It just keeps on going up like this at a super fast rate, ever increasing rate. So you could keep going forever to the left and get closer and closer and closer to 0 without quite getting to 0. So 5 to the negative billionth power is still not going to get you to 0, but it's going to get you pretty darn close to 0. But obviously if you go 5 to the positive billionth power, you're going to get to a super huge number, because this thing is just going to keep skyrocketing up like that. So I'll just draw the whole curve to make sure you see it. Over here, I'm not actually on 0, although the way I drew it might look like that. But I'm slightly above 0. I'm increasing above that, increasing above that. As once I get into the positive x's, then I start really shooting up.
Okay. So, okay, one of the first things we want to take a note is the values when we are making our table. So let us use y equals 5 to the x as he was using. And so we can have some values. This is our x and our y. -2, -1, 0, 1, 2. Well, this would be, we know because it's a negative amount, it would be 5 to the -2. And so that's equal to 1 over 5 squared. That's equal to 1 over 25. The next one will be 5 to the -1. That's going to be 1 over 5. Anything to the 0, 5 to the 0 is equal to 1. Now, I wanted to take a note that when we talk about an exponential function, every exponential function passes through the point y equals 1. Every exponential function passes through the point y equals 1. Every exponential function passes through y equals 1. Every exponential function. Okay? And another point to note, when x is positive, that's greater than 0, that means same as positive, the function increases rapidly. Okay, so that's what we are looking at. So to get a new page now, when we have a function like this, for f of x is equal to 5 to the x, it would run something like this. And we know that this is always y is equal to 1. Okay, so we could even look at it on another okay, so here we have y equals 2 to the x. So let's see what that looks like. Y equals 2 to the x. So here it is. Okay, so we can see that y equals 2 to the x gets closer and closer to the x-axis. We call this an asymptote. This here is called an asymptote as it gets closer and closer to the x, and notice it passes through the 1. And if we were to look at it on a bigger scale, we'll see that it seems to be on the line. But an asymptote is actually a line that gets closer and closer to a value but never ever touches it. Okay, so that's what we mean by that. So let's go to
The Cozy Car Company ships some of their new cars to Japan and Vietnam. The number of cars that will be shipped to Japan during the next T months is modeled by the function j of t is equal to 2 to the tth power. The number of cars that will be shipped to Vietnam during the next T months is modeled by the function p of t is equal to 2t squared. Which country had received more cars from the Cozy Car Company after 5 months, or will have received after 5 months? So let's see how much Japan is going to receive after 5 months. So t is in months, so j of 5 is going to be equal to 2 to the 5th power, which is equal to 2 times 2 times 2 times 2 times 2. And let's see, 2 times 2 is 4, 8, 16, 32. So Japan will have received 32 cars, and Vietnam, so V of 5 is going to be 2 times 5 squared, which is going to be 2 times 25, which is equal to 50. So based on these two models for how much they're going to receive after T months, after 5 months, Vietnam is going to receive more cars. So I guess the answer to that is Vietnam. Vietnam will have received more cars after 5 months. Which country had received more cars from the Cozy Car Company, or will have received more cars after 7 months? So once again, let's try this out. J of 7 is equal to 2 to the 7th power. Let's see, 2 to the 6 is going to be 32 times, this is 2 to the 5th, times 2 times 2, which is going to be equal to 32 times 4, which is 128 cars after 7 months will have gone to Japan. And to Vietnam, V of 7 is going to be equal to 2 times 7 squared, so that's equal to 2 times 49, which is equal to 98 cars. So after 7 months, Japan would have received more cars. So Japan will have received more cars after 7 months. So this is interesting. We see that the exponential function, notice, where you have the t as the exponent, that although it might start off a little bit slower than this, it's essentially a quadratic function, you have something squared. It starts off slow. After 5 months, you would have shipped fewer cars than using the quadratic model right over here. But then it more than catches up, and it starts to increase at a faster and faster rate. And even by 7 months, it's able to pass up the quadratic function. Which country will have received more cars from the Cozy Car Company? Will the country which received more cars from the Cozy Car Company after 7 months continue to receive more cars than the other country in future months? Yeah, absolutely. Once the exponential function passes up the quadratic function, it just goes faster. It just keeps increasing at a faster and faster rate. And you can see that if we wanted to compare 8 months, so j of 8, this is the exponential function, this would be 2 to the 8th power. This times 2, they'd get 256 cars. And v of 8 is going to be 2 times 8 squared, which is 2 times 64, which is 128. So notice now we would have shipped twice as much to Japan as Vietnam, which isn't what the case, right? Okay, we ship more to Japan than Vietnam, but not twice as much. And we could keep going. We could, if you want, you could go to J of 9. J of 9 is 2 to the 9th power. It's going to be 256 times 2 of 512 cars, while V of 9 is going to be 2 times 9 squared, which is 2 times 81, which is 162. So now it's way more than double, actually more than triple. So you see that once you get past those initial 2 months, the exponential function is increasing at a much faster rate. And we can actually visualize it. Let's actually get our graphic calculator to visualize these two things to see how that is happening. So it's graphic. So the first one, let me graph the exponential. So 2 to the, well, I'll just say x power. We'll say x is our independent variable here. So 2 to the x power. And then let's do the quadratic one. This is y2, it'll be v of 2. Let's say 2 times x squared. Now let me set the range. So let me set the range here. So let's see, let's say x starts at 0, and then let's say it goes up to 10. Let's say it goes up to 10. The x still could be 1, x still could be 1. Now y's minimum, let's say this will start at 0, and then y max, let's go with 1,000. Let's go with 1,000. Let's make the y scale 100. 100. And now I think we're ready to graph. So let's graph this and see what happens. So let's punch in on things. So that right over there, that's the exponential. And then there you see right over there you have the quadratic. Actually, let me zoom in a little bit on this so that we can see where they pass. Actually, let me zoom in a little bit on this box so that we can really see. We can see where they, or attempt to see where they pass each other up. So I'm going to start there. I'm going to make my box. Let's see, go. Whoops. It's weird using a calculator on a computer like this. But you definitely see, even what we've already graphed, that the exponential really just starts to shoot up while the quadratic is just going, well, it's still increasing at a decent pace, but nowhere near as fast. And the difference is becoming more and more pronounced as time increases. Just make sure that's as low as that, and let's graph over in this range right over here. So let's see, that right over there, that's the exponential function, that's 2 to the t power. And then that right over there is the quadratic. So you definitely see that earlier on the quadratic has higher values, and you see that right over here. After 5 months, we ship more cars to Vietnam. But then the exponential passes it up and then just keeps shooting faster at an ever-increasing pace.
Okay. Let's go.
Let's do a couple of word problems dealing with exponential growth and decay. So this first problem, suppose a radioactive substance decays at a rate of 3.5% per hour. What percent of the substance is left after 6 hours? So let's make a little table here to just imagine what's going on. And then we'll try to come up with a formula for, in general, how much is left after n hours. So let's say hours that have passed by and percentage left. Percent left. So after 0 hours, what percent is left? Well, it hasn't decayed yet, so we have 100% left. After 1 hour, what's happened? Well, it decays at a rate of 3.5% per hour. So 3.5% is gone. Or another way to think about it is 0.965. Right, or remember, if you take 1 minus 3.5%, or if you take 100% minus 3.5%, So each hour, we're going to have 96.5% of the previous hour. So in hour 1, we're going to have 96.5% of hour 0, or 0.965 times 100 times hour 0. Now what happens in hour 2? Hour 2. Well, we're going to have 96.5% of the previous hour. We will have lost 3.5%, which means that we have 96.5% of the previous hour. So it'll be 0.965 times this, times 0.965 times 100. I think you see where this is going in general. So in the first hour, we have 0.965 to the first power times 100. In the 0th hour, we have 0.965 to the 0th power. We don't see it, but there's a 1 there, times 100. In the second hour, 0.965 to the second power times 100. So in general, in the nth hour, this is a nice bold color, in the nth hour, we're going to have 0.965 to the nth power times 100 left of our radioactive substance. And oftentimes you'll see it written this way. You have your initial amount times your common ratio, 0.965 to the nth power. This is how much we're going to have left after n hours. Well, now we can answer the question. After 6 hours, how much are we going to have left? Well, we're going to have 100 times 0.965 to the 6th power left. We can use a calculator to figure out what that is. Let's use our trusty calculator. So we have 100 times 0.965 to the 6th power, which is equal to 80.75. This is all in percentages. So it's 80.75% of our original substance. So 80.75%. Let's do another one of these. So we have Nadia owns a chain of fast food restaurants that operated 200 stores in 1999. If the rate of increase is, actually, there's a typo here, 8%. The rate of increase is 8% annually. How many stores does the restaurant operate in 2007? So let's think about the same thing. 1999. So let's say years after 1999. And let's talk about how many stores Nadia is operating her fast food chain. So in 1999 itself is 0 years after 1999, and she is operating 200 stores. Then in 2000, which is 1 year after 1999, how many is she going to be operating? Well, she grows at the rate of 8% annually. So she'll be operating all of the stores that she had before, plus 8% of the stores she had before. So 1.08 times the number of stores she had before. And you're going to see the common ratio here is 1.08. If you're growing by 8%, that's equivalent to multiplying by 1.08. Let me make that clear. 200 plus 0.08 times 200. Well, this is just 1 times 200 plus 0.08 times 200. That's 1.08 times 200. Then in 2001, what's going on? This is now 2 years after 1999. You're going to grow 8% from this number. So you're going to multiply 1.08 times that number times 1.08 times 200. I think you get the general gist. If after n years after 1999, it's going to be 1.08, let me write it this way, it's going to be 200 times 1.08 to the nth power. After 2 years, 1.8 squared, 1 year, 1.8 to the first power, 0 years, this is the same thing as a 1 times 200, which is 1.08 to the 0th power. So they're asking us, how many stores does the restaurant operate in 2007? Well, 2007 this is 2007 is 8 years after 1999. So here n is equal to 8. So let us substitute n is equal to 8. The answer to our question will be 200 times 1.08 to the 8th power. Let's get our calculator out and calculate it. So we want to figure out 200 times 1.08 to the 8th power. She's going to be operating 370 restaurants, and she'll be in the process of opening a few more. So she's going to be, if we round it down, she's going to be operating 370 restaurants. So 8% growth might not look like something that's so fast or that exciting, but in under a decade, in only 8 years, she would have got her restaurant chain from 200 to 370 restaurants. So for over 8 years, you see that the compounding growth by 8% actually ends up being quite dramatic.
Alright, so you're going to work this out. This Mercy owns a chain of Rubis gas stations that operated 400 pumps in 2014. If the rate of increase is 7% annually, how many pumps will this Mercy operate in 2020? Let's go. So, what's the result? What should we write first? Should we draw a table? Yeah, let's draw a table. Yeah. And so we would put what? Pumps. P-U-M. It looks like pumps, right? Pumps 2014. And what we put here? Years?
No, it's years 2014 like pumps. 400.
Oh, okay, so good. Okay. So it's going to be years and pumps. Oh, this is not right. It's P-U-M-P-S. Okay. What next? What do we write? 2014.
0.
Do we put what here? 0?
0 to the side. 400.
400. Yes. 2015. What do we say now?
1 year.
So it would be 1 year. 1 year has passed. So it would be?
1.07.
So it would be 1.07 times 400. Okay, so 2016. 2016, that would be 2 years. So it would be 1.07 times 1.07 times 400. Okay, do we still have to continue? Okay, so n then. So for n years, what do we do? It will be for n, what do we write? It will be 400 times 1.07 to the n, right? And then now time now is going to be how many years? Are you sure? Check it and make sure you know how many years. So 2014 is year 0, year 1, 2016 is year 2, 17 is year 3, 18 is year 4, 19 is year 5, 20 is year 6. So for n equals 6, so for n equals 6, it will be pumps equal equal 400 times 1.07 to the 6th power, which gives us what? Which gives us, you don't have to put this in a calculator. Or you could have just put 400 times 1.071 times, times 1.072 times, times 1.073 times. So you can just put x to the y and then put 6. 400 times 1.07 press, and we can't have 0.292 over, so 600 pumps. Yeah, so that would be it, okay? So let's go again. So for year 1, 2014, that's year 0, that's your zeroth year, 400 pumps. 2015, the first year, so it's 1.07 times 400. For year 3, 2016, year 2 rather, 2016, it's 1.07 times 1.07 times 400. Notice it's 1.07 times the year 1 amount. And so we just go straight to year n. So for n years, it's going to be 400 times 1.07 to the n. Now, for n is equal to 6, how did we get n equal to 6? N is equal to 6 because from 2014 to 2020 is 6 years. So the pumps will be equal to 400 times 1.07 to the 6. And when we calculate, we get 600.29, but we can't have 0.29 of a pump because that will, round it down to the, not up, down to the pump. 600 pumps. And that's good. So we say then that $300 is left in the bank for 7 years. It grows at a rate of 3% per annum. What is the total after 7 years? Well, we know that the total, let's call it the amount A, is going to be equal to 300 times 1.03 to the n, where n equals 7. So we could just put 7. And that's it. So let's do that. So 300 times 1.03 to the 7. Okay? And the answer is 368. 368.96. Okay? So it's 368.96 after 7 years. Okay? And then we're going to move on. So
Cesium-137 is a radioactive tracer element used to study upslope soil erosion and downstream sedimentation. It has a half-life of approximately 30 days. So this half-life of 30 days, this means that if you were to start with, let's say if you were to start with 2 kilograms of cesium-137, that 30 days later, you're going to have 1 kilogram of cesium-137, and the other kilogram has decayed into other things. Assume, and if you waited another 30 days, you would have half a kilogram of cesium-137. Assume that the amount A in becquerels of cesium-137 in a soil sample is given by the exponential function A is equal to C times R to the T, where T is the number of days since the release of cesium-137 into the soil, and C and R are unknown constants. amount of some element, I probably think in terms of mass, and I might talk in terms of kilograms. But some people might also be referring to the amount of this radioactive substance in terms of the amount of radioactivity it produces. And becquerels is the international unit of radioactivity, named after Henry Becquerel, who co-discovered radioactivity with Marie Curie. So you could consider this the amount of cesium-137 that causes a becquerels of radioactivity. But either way, we can just think of it as a quantity. But it's really the quantity that causes a becquerels of activity. So just to be clear, the amount is given by the exponential function a is equal to, let me just rewrite it, a is equal to c times r to the t power, where t is the number of days since the release of the cesium-137 in the soil, and c and r are unknown constants. Fair enough? So let's just be clear, this is days since release. In addition, assume that we know that the initial amount of cesium-137 released in the soil is 8 becquerels, Solve for the unknown constants c and r. So the initial in the soil, that's when t is equal to 0, when no days have passed. So we could say that the amount at time 0, well, that's going to be equal to c times r to the 0 power, which is just going to be equal to c times 1, which is equal to c. And they tell us what a of 0 is. They say a of 0 is 8 becquerels. So this is going to be equal to 8. So our constant here, the c, is just going to be equal to 8. What is the value of the constant? We can just write 8 right over there. Then they ask us, what is the value, so the value of the constant c is 8. What is the value of the constant r? Round to the nearest thousandth. So we're starting with 8. So a of 0 is 8. How much are we going to have after 30 days? The reason why I'm picking 30 days is that is the half-life of cesium-137. So a of 30, remember our t is in, let me just switch colors just for fun. Remember t is in days. So a of 30. So after 30 days, I'm going to, this is, if I want to use this formula right over here, if I wanted to use the description of this exponential function, we already know that c is 8. It's going to be 8 times r to the 30th power, which is going to be equal to what? Well, if we started with 8, 30 days later, we're going to have half as much. We're going to have 4 becquerels. We're going to have 4. And now we can use this to solve for r. So you have 8 times r to the 30th power is equal to 4. Divide both sides by 8. You get r to the 30th power is equal to 4 over 8, which is the same thing as 1/2. And then we can take the 1/30th, we can raise both sides to the 1/30th power. R to the 30th, but then then you can think of the 30th root of that, or raising that to the 1/30th power. That's just going to give us r is equal to 1/2 to the 1/30th power, and that is something that's very hard to.
Yeah. Okay.
Later for that, they hint that we're going to round to the nearest, thousand, so let's get the calculator right out. And so we're talking about 1/2 to the 1/30 power. 1/30 power. So we get 0.9771599, keep going. But they tell us to round to the nearest thousand, so it's 0.977. 0.977, rounded to the nearest thousand. And then they finally say, how many becquerels of cesium-137 remain in our sample 150 days after its release in the soil? Use the rounded value of r and round this number to the nearest hundredth. So just to be clear, we now have we already know c and r. We know that the amount of cesium-137 in becquerels as a function of time and days is going to be equal to 8 times 0.977 to the t power, where t is the number of days that passed. And they're essentially saying, well, how much do we have left after 150 days? So they want us to calculate what is A of 150? Well, that's going to be 8 times 0.977 to the 150th power, And so clearly we need a calculator for this. So let's calculate that. So it's going to be 8 times, and they told us to use our rounded value of R, not the exact value of R. So it's going to be 8 times 0.977 to the 150th power. And that gets us point, and they want us to round to the nearest hundredth, 0.24. 0.24 is in fact 0.24 becquerels is kind of the radioactivity level of the cesium-137 that we have left over. Now, one interesting thing is they asked us to use the rounded value of R, so we use the rounded value of R. But you could, because this right over here is a multiple of 30, you can actually, not too difficult a way, find out the exact value that's left over. And actually, you don't even need a calculator for it. I encourage you to pause your video and try to think about it. Find the exact value. Well, instead of writing 0.977, let's write A of t as being equal to 8 times our R. This is an approximate value for R. If we wanted to be a little more exact, we can say that our R is 1/2 to the 1/30th power, and we're going to raise that. We're going to raise that to the t power, or we could say A of t is equal to 8 times 1/2 to the t over 30 power. If we raise something to an exponent, then raise that to an exponent, we can take the product of those exponents. So that's 1/2 to the t over 30 power. We actually put that in another color, in yellow. So that's 8 times 1/2 to the 1/2 to the t over 30 power. 1/2 to the t over 30 power. Which this parentheses right over here. This is another way to describe A of t. So what is A of 150? So A of 150 is going to be equal to 8 times 1/2 to the 150 over 30. Well, that's just 5. 1/2 to the 5th power. Well, what's 1/2 to the 5th power? That is 1 to the 5th over 2 to the 5th, or 1 over 32. So this right over here is 1 over 32, which is equal to 8 over 32. 8 over 32, which is equal to 1 over 4, which is equal to 1 over 4, or 0.25, or 0.25. So using our approximation for R, we got 0.24. We rounded to the 150th power. So it's using our approximation a lot. We're multiplying. We're taking 150 of these and multiplying them together. But it's not too far off of what the real value is. So they asked us to use the rounded value, but if we use the precise value, the actual value, we would have got 0.25 becquerels would be left over.
Okay, so